Hello, students. Welcome. Good morning. So, we were doing periodic table. So, today's topic, uh, if in the last lecture, if you watched out, I've given you an overall introduction about the periodic table, the rows and groups, and on what properties are the different periodic properties are there, what are the different properties, the trends, rather whose trends are actually measured, what trends actually mean, rather. If I'm going to repeat that one, trend means actually the variability. Okay, so it's all about that how a particular parameter, that means individual property, there are a list of properties given over there. So though those are not the only properties within the periodic table, there are other properties too. But for this time, for this class, and for according to the current scenario or the syllabus, we will stick to this for these properties only. That's enough to rather to carry on with the periodic table. All right. So if the periodic table, the trends basically represents the variability. So variability, that means how it varies from one particular point to another particular point. So that's what you call as periodic trends. All right. So regarding periodic trends, we will consider today one very important parameter, or rather one of the property to consider, rather to analyze the trends of that particular one. So our today's topic of discussion is ionization potential. So today's topic of discussion is ionization potential. Though rather by the word itself, you may think that it's a very heavy-weighted word. All right. Oh my God, that's very maybe very tough. No, no, no. Don't panic. I really assure you, don't panic. The nothing to panic about. Any properties or whatever, you should not panic. Just follow the sequence and just try to understand how the basics goes on, and then you will understand that all the properties are quite easy and easy to analyze. Very easy to analyze. Yes, of course, very easy to analyze. So for this, we need by this. So you must have known that basics of the some of the basics of periodic properties. So all right, I'll go to the basics of the periodic properties while discussing this one later. First, start with the very initials. Okay, we'll go by step by step. We're not going to hurry up. We're not going to jump here and there. No, not going to do any sort of things. We're going to just go step by step. All right. Though it's over here, periodic properties represented by as a one arrow. Please, that's basically toward today's purpose. That today's discussion is based on ionization potential, and for that reason, only one arrow given. All right. Don't be confused with this point. Okay. The first question obviously arises, what is ionization potential? Right? That's a very obvious question. With the word itself, I always say try to understand the meaning of this word or any word when a new word comes up. It will be easier to understand the the background of that one, that what exactly the things are going to tell us and what exactly we are going to analyze and understand. Okay? Potential. What's the definition? What is this? Ionization potential is the minimum amount of energy required to remove an electron from the valence shell of a neutral gaseous atom and convert it into a positively charged gaseous ion. My God, such a big definition. Okay, let's analyze, all right, let's look into this like this way. You're having an atom, okay? We know it's a neutral one. Fine, very good. It's a neutral one, you're having an atom. Now we know that that particular atom can be of a solid substance, can be of a semi-solid, that means of a, or neither a solid nor a liquid, rather, or a semi-solid substance. It can be of let's forget a semi-solid. Focusing on three states of matter only. It can be of a solid substance. It can be of a liquid substance. It can be of a gaseous substance. Right? We know that matter is made up of, by this time, by this time we are confirmed that matter is made up of atoms. Okay, and definitely furthermore electrons, protons, and neutrons. Clear? Now, the first, we are having an atom. We need to think. We need to think that what this atom belongs to, which particular state of matter, whether it's of the solid substance, liquid substance, or gaseous substance. Whatever the substance is, let us consider that one as a solid substance. Okay, that atom belongs to this particular atom we have considered, and this atom belongs to a solid substance. Very good, no problem. Then what I'm going to do is that atom, it's neutral. We know this. By this time we know that atoms are neutral in nature, neutral in terms of electrical neutrality. Okay, electrical neutrality. We are focusing on this. So atoms are electrically neutral. All right, very nice, fine enough. The next, so neutral atom we have taken. What I'm interested is, I am interested to make this a neutral atom into a charged atom, charged, positively charged. How that is possible? Positively charged. Okay, I am interested to make this one into a positively charged. Okay, now this positive charge is possible by two ways. This possibility of converting this one into the positive charge species by two ways. Either I have to remove that one, either I have to add the proton into that one, or I have to remove an electron. Two ways are possible. If I remove an electron, then the atom will be of positively charged. And if I add a proton, it will be of positively charged. But when it's a condition, when it's a question of ionization potential, I want to convert that. This term is added to this. Okay. Now the first one, rather, that addition of proton, that condition become invalid. Okay, that condition becomes invalid when the term is ionization potential. Okay, so what I'm going to do is I have to remove an electron. That's the only procedure, or the only step that is accepted with ionization potential. So this is basically what I'm going to do. What I have to do is I have to remove an electron from the neutral gaseous atom. So just remember, we have taken an atom of a solid substance. But another condition is whether it's a solid or a liquid or whatever, we have to convert that one into gaseous state. Okay, whichever the atom or the element is, we have to convert that one into gaseous state. And then that one we will convert it into a positively charged gaseous ion. So normally it's not possible. Normally, a neutral atom will not normal neutral atom will not leave electrons so easily. So what needs an external force, and what the external force is, it can be anything. Over here, external force is some sort of energy. So if we sort of energy of consideration over here, let's find it out. If we give energy over here, we are having this. So if we are giving energy over here, well, that energy will be accepted first, definitely the valence shell, because removal of electrons from the valence shell is quite easy compared to the electrons present inside the inner shells, because they are buried inside. Since they're buried inside, so it becomes quite difficult to take out an electron from the inner shells from the inner shells. It will be quite a tough one. But it's quite easy one to remove an electron. From where? To remove an electron from the valence shell. That means the outermost shell. Availability. That means they are exposed outside. What should I say? The face-off between energy and electrons will be that will be faced by the outer electrons first. All right. So when the outer electrons accepts energy, and it's not that only the outer electrons accept energy, all the electrons accept energy. But the point is the tendency that the outer electrons are already there outside, they're away from the nucleus. So their chances of leaving the um, atom becomes very easy compared to the other electrons. All right. Now, what happens? There's in the balance shell, you can see two electrons are there, and one of the electron is not there. One of the electron is not there. So this is converted. This has become a positively charged ion, positively charged ion, a positively charged atom rather. But better to say positively charged atom. So known as cation. And along with that, what's happening? What I'm having? The electron, the released electron. Okay, what I'm having? The released electron. So this supply, this energy which is being provided to the neutral atom from outside, that E is known as, that particular E is known as ionization energy. Okay, that particular E is known as ionization energy. Okay. Now this ionization energy, these are other names also, ionization potential, ionization energy, or ionization enthalpy, all these are common, all the names of a particular thing. It's the same parameter, that's ionization potential, or it's termed as ionization energy, or it's also termed as ionization enthalpy. So all these are the names of the same particular parameter. That's the energy required to convert any neutral gaseous atom into a positively charged gaseous ion. That's all. I hope it's clear till this much. Not so tough. Okay. Now the question is, what are we going to do with it? What are we going to do with this? How are we going to analyze? We just have the energy, rather, how this will be applicable? Okay. Let's move on to that section. Ionization potential analysis. Okay, ionization potential analysis. Analysis are of two types, group-wise and period-wise. So when we are going for periodic table, we are having two sets of analysis, or there are two ways or trends of analysis. One is the group-wise, another one is the period-wise. So group-wise, down the group, and period-wise, along the period left to right, or it's basically down the group or up the group or along the period right to left. And yeah, so it's if we go by group wise, it can be down the group or up the group, or if you go by period wise, along the period. Basically, along the period, there are two options, so we have to consider both. Either it will be from left to right, or either it will be from right to left. So today we are going to analyze ionization potential variability, considering all these possibilities of analysis. All right? So let's jump onto that section. We're having periodic table over here, and if you remember the horizontal sections, as the horizontal the boxes were there, you can see in orange colors. It's basically the rows, the horizontal lines, and the vertical columns are called the periods. Sorry, the groups. The horizontal line, the boxes are called the periods, and the vertical boxes are called the groups. So now, moving on to our analysis section. Question, of course. Now the question, what happens down the group? This is the question, right? What happens down the group? We have considered ionization potential, and what happens down the group? Let's find it out. What happens down the group? The first down the group, what do we notice? Atomic number increases, isn't it? We always notice atomic number increases down the group. It's clear? We're absolutely clear. Fine. Moving on to next. If atomic number increases, then what we will encounter, what we will observe, what is our observation? Our observation is nuclear charge increases and number of orbits increase. Isn't it so? Don't you think that nuclear charge increases? It's obvious. Nuclear charge increases because if atomic number increases, then the number of protons increases, and parallelly, number of orbits increases. Right? All right. Okay. Then number of orbits, because why number of orbits increasing? Because the number of electrons will also increase. Number of electrons will also increase, and hence, with just a mere increase in atomic number nuclear charge increases and number of orbits increases down the group. Just focus. This is I'm considering, or rather, we're discussing about down the group from up to the bottom. We're coming down the bottom of the periodic table. All right. Next, if this happens, then what? Okay, if this happens, then what? Let's find it out. Atomic radius increases. Don't you think so? Don't you think so? Atomic radius will increase if the number of orbits increase. Don't you think that atomic radius will also increase? Because if the number of orbits are increasing, the distance between the valence shell from the nucleus, it increases. Now you can tell me, sir, this is actually the central nuclear charge. The nuclear charge also increases. Then will they not be pulled closer to the nucleus? Yes, that's a very obvious question. That's a very obvious question. That a nuclear charge increases down the group. That's acceptable, and it will pull the electrons towards itself. You're focusing on the effective nuclear charge. That's no problem. But what happens over here is down the group when the number of orbits increases. With increasing the number of orbits, this orbit increase that actually dominates this parameter. That increase in the number of orbits, this actually dominates over the nuclear charge increase. And for this reason, since the number of orbits dominates, so the effect of nuclear pull over the atomic radius, or effective nuclear pull over the atomic radius, is less, and hence there should have been a decrease, but the decrease is very less. So the prominent is what dominates is the number of orbits increase, so the radius increases. The radius increases. Okay. So if the radius increases, distance between the nucleus and the valence electrons also increases. Isn't it so? If the radius increases, the distance between the nucleus and valence electrons will also increase. Valence electrons, the outermost orbit. So radius will increase, the distance between the nucleus and the valence electrons will also increase. Yes, of course. Okay, if that happens, then what is the reason? Then what will happen? If this happens, then effective nuclear pull over the valence electrons decreases. They're away from the nucleus. So will the nucleus will be able to pull the valence electrons so firmly? Can you just think about it? That if anything which is far away from you, can you pull them very tightly, very firmly? Or the things which are closer to you, can pull them very firmly or hold them very firmly? Which one happens? The things which are closer to you or things which are far away from you? Or if the things which are going away from you, can you pull them very firmly compared to those things which are closer to you? Of course, which are closer to you, you can hold them, you can pull them firmly, rather than those who are away from you, right? So the same thing happens over here. The nuclear pull over the valence electrons decreases, and what happens? What happens? The nuclear pull valence electrons decreases, and thus they are not being able to hold the electrons very firmly. What's the result? The result is less energy required to remove an electron from the valence shell. Less energy required to remove an electron from the valence shell. That's the thing happens. Isn't it? So if they're away, they're not being held together, rather the electrons are not being pulled by the nucleus firmly, very strongly, then, well, do you think that a lot of amounts of energy will be required to remove them from the valence shell? Do you think so? A lot of amount of energy is required to remove an electron from the valence shell. A lot of amount of energy. No, less energy required because they're just loosely attached. So just just a small amount of energy is enough to remove them from the valence shell, and hence ionization potential decreases. Ionization potential decreases. Clear, everyone? Okay, so let's do one thing. Let's do a validation. Let's do a validation. So we are having a group. We are having a group over here, group one. So you can see down the group lithium, sodium, potassium, rubium, cesium, francium. So atomic numbers over there 3, 11, 19, 37, 55, 87. So the first we are going to go with atomic number increases. It's quite visible. You can see Z equals to 3, 11, 19, 37, 55, 87. Down the group, atomic number increases. Right? Moving on to the second. Nuclear charge increases, number of orbits increases. Nuclear charge plus 3, plus 11, plus 19. Number of orbits increases. Okay, I'll come to that one also. Atomic radius increases. We have seen that if the number of orbits increase, I explained that one also previously. If the number of orbits increases, then the atomic radius will also increase. And this is how. Number of orbits, Z, this is the atomic numbers, and with the orbits, K, L. Then 11, K, L, M, with 19, K, L, M, N. And it goes on like that way. K, L, M, N, O. So these extensions, or these rather things suggest that the number of orbits increases. Clear? So that's definitely the atomic radius will also increase. What next? Distance between the valence electrons increases. Obviously, now the valence electrons means the electrons present in the L shell, M shell, N shell. These are the valence shells, so electrons present in the valence shell. Now, if L shell, N shell, M shell, they are going away from the nucleus. So, with as you can see, the valence shell is going away from the nucleus. So, definitely the valence electrons will also go away from the nucleus. The distance increases. If distance increases, and you can see the valence shell L, M, N. So they are going, the distance increases away from the nucleus. So effective nuclear pull of the electrons decreases. Effective nuclear pull of the electrons decreases. And thus, if the effective nuclear pull decreases, so less energy required to remove an electron from the valence shell, and ionization potential decreases. So ionization potential decreases down the group. Okay. Now coming to what happens up the group. So we have done down the group. So we will just follow the reverse. We'll go by down the group. Down the group again. Now, sorry, up the group, atomic number decreases. Obvious. So because if down the group atomic number increases, up the group atomic number will decrease. Then, if atomic number decreases, nuclear charge decreases. And if along with the nuclear charge, number of orbits also decreases. Obvious. Atomic number decreases, number of nuclear charge decreases, and number of orbits also decrease. This means atomic radius will decrease. If atomic radius decreases, then what will happen? Distance between valence electrons will decrease. Distance between valence electrons will decrease. And if distance between valence electrons decrease, then the nuclear pull, the attractiveness of the valence electrons will also increase because they will go closer to the nucleus, right? If you remember, this was just the opposite in the previous case. Down the group, it was just the opposite, right? Isn't it? So valence electrons, it was previously increases and the effective nuclear pull was decreasing. So it was just a reverse up the group. And hence, if the nuclear pull of the electrons increases, the more energy required to remove an electron from the valence shell, which thus means the ionization potential increases. So it's just the reverse, the opposite. So down the group, ionization potential decreases, and up the group, ionization potential increases. We will validate Again, we will validation. We are having the group over here. Atomic. So as you can see, the values are decreasing. And that means nuclear charge decreases, number of orbits decreases, as you can see, plus 19, plus 11, plus 3. So we're focusing on this lower, these atomic numbers. Those are higher atomic numbers, basically 87, 55, 30 are higher atomic numbers. So just focusing on the atomic numbers with just which are there in the present syllabus, as per the present syllabus. So it's having atomic radius decreases. Atomic radius decreases of the group because K as you can see over there, atomic radius decreases because the number of orbits will decrease, right? As you can see, the number of orbits decreasing. 19 KLM, 11 KLM, 3 KL. So it's going down. The numbers are decreasing. The radius decreases, and hence the distance between valence electrons decreases. Distance between valence electrons decreases, which means the distance between valence electrons, as you can see, from 19 it was N, then M, then L. Just the reverse. I'm doing just the reverse. It's the opposite. And hence effective nuclear pull over the electrons increases, and that means more energy required to remove an electron from the valence shell, and that means ionization energy increases. So ionization energy, ionization potential increases, right? Okay, moving on to the next, we are having along the period. Target is along the what happens along the period. Let's find it out what happens along the period. The condition is given over here from left to right. So along the period, as I said many times, and I always say you should mention when you're going for along the period analysis that whether it's from right to left or whether it's from left to right, you should mention that because that's very important. From left to right or right to left, you should mention that one. That is very, very important. The first, from left to right, atomic number increases. From left to right of periodic table, atomic number increases. Then what happens? If atomic number increases, nuclear charge increases, but there is a twist. The number of orbits remains the same. Number of orbits remains the same, which means effective nuclear pull over the valence electrons increases. Effective nuclear pull over the valence electron increases. Because nuclear charge increases, number of orbits remaining the same, the overall nuclear charge over the valence electrons increases. That's called the effective nuclear pull. The effective nuclear pull, if it increases, that means atomic radius will decrease. And if atomic radius decreases, then the distance between the nucleus and the valence electrons also decreases. And if this happens, then more energy is required to remove an electron from the valence shell. And thus, ionization energy increases. So ionization energy increases. So along the period from left to right, ionization energy increases. Okay, we'll do the validation, of course. We're having this period number 2. And what are the atomic numbers there? 3, 4, 5, 6, 7, 8, 9, 10. So atomic number increases. As we can see over there, atomic number is increasing. Atomic number is increasing. So nuclear charge increases, so as we know that with the increase in the atomic number, the nuclear charge also increases, but the number of orbits remains the same. Number of orbits remains the same. So if you remember, that was atomic number, the electronic distribution, 2, 1, 2, 2, 2, 3, 2, 4, and it goes on like that way. So atomic numbers, the number of orbits remains the same. It's not changing. Then, if this happens, then effective nuclear pull over the valence electrons increases. So the effective nuclear pull, that means the density, its effect. So it overpowers the electron the electron distribution. It overpowers the increase in the number of electrons because electrons are scattered, and hence it overpowers, and thus it pulls. So the nuclear pull is greater. It overpowers and it brings the electrons closer to the nucleus, and thus atomic radius decreases. And if atomic radius decreases, the distance between the nucleus and the valence electrons also decreases. And if this decreases, then more energy is required to remove an electron from the valence shell, and thus ionization energy decreases. So in all the period from left to right, ionization energy increases. So ionization energy from left to right, ionization energy from left to right increases. Similarly, along the period from right to left, just the opposite. Atomic number decreases, nuclear charge decreases, number of orbits remains the same, so effective nuclear pull over the valence electrons decreases. Atomic radius increases, which means the distance between the nucleus and the valence electrons also increases, which means the less energy is required to remove an electron from the valence shell, and thus ionization potential decreases. So from right to left, ionization potential decreases. We'll do the validation, of course. We're having the period, and we can see from left to right, from right to left, it's decreasing from 10, 9, 8, 7. It's decreasing. The values are decreasing. So the nuclear charge decreases, number of orbits remain the same. Effective nuclear pull over the valence electrons decreases, and thus atomic radius increases. Because if the pull is decreasing, the radius will obviously increase. And if the radius increases, then the distance between the nucleus and the valence electrons also increases. And if this is so, then less energy is required to remove an electron from the valence shell, and thus ionization potential decreases. So this is all about ionization potential, and we conclude that ionization potential is minimum for the alkali metals, that's group 1 elements, 1A, which have single electron outside a closed shell, and it generally increases across a period from left to right of the table. The noble gases have high values of ionization potential in comparison to the rest of the elements of the period. Because in noble gases, they are complete octates over there, filled shells. It's very difficult to remove an electron from inert gas, or the valence shell of inert gases. So that's all for the ionization potential and ionization energy. I hope it becomes clear to all of you, with no doubts, of course. So, but if you're having confusion or any doubts, you are free to ask questions or mail your questions to the following. So till then, I will take leave from you all. So thank you so much, and stay safe and take a very good care of yourself, and me signing off for now. Thank you.